Talk about ab-initio theories of spontaneous emission from gain media. And this was work done at MIT with my advisor, Stephen Johnson, and Doug Stone, and several people. Maybe I'll say at the end which people contributed to it. Okay, so the talk will be about electromagnetic fluctuations, noise, and radiation, which is important in many things in physics, like thermal radiation, fluorescence, Casimir forces between bodies, and lasers. And I'll talk about specific cases. Now, the general goal of this field is to find the fluctuation spectrum. That's what we want to know. And the approach that we use and many people use is to solve first the noise-free problem and then to treat noise as small perturbations around the steady state. So the computational tools that we will need is the Green's function for the noise-free problem or any solution. And then we also will need something to describe the correlations of the noise. And we'll use the fluctuation dissipation theorem. So that's the general topic, and what I'll show today is what I did in this area. And so the general situation we'll consider is to find fluctuation spectra of resonators, which are non-emission and can have some losses and some gain. And I'll talk about two things. In the first part of the talk, I'll describe the situation. The two poles of the Green's function collide at exceptional points, what Doug was saying that I'll talk about. And then in the second part of the talk, we'll consider the situation when we add enough gain to the system that a pole reaches the axis, the real axis, and the system begins to laze. And we'll talk about what noise does in that case. And the effect of noise is to broaden the resonance peaks, and we'll see how to calculate that width. So with that, let me start with the first part of exceptional points in the Green's function. So my motivation for studying this was this paper, a very nice paper by Barry in 2003. And he studied the Linewidth of unstable resonators, which are basically these open resonators that you see here a demonstration. Basically, they're characterized by the fact that a lot of radiation leaks out in each round trip. And he noticed some peculiar emission properties when these resonators have exceptional points. So the quantity he evaluated is the Peterman factor, which is an enhancement factor in the Linewidth. It's defined here if psi is the lasing mode or here the transverse mode. The Peterman factor is just the ratio of the conjugated inner product and the unconjugated inner product. And you see that when this k is plotted as a function of the Fresnel number, which is something proportional to inversely proportional to the distance between the mirrors, so you sweep the distance between the mirrors like that, and you see these spikes in the Peterman factor. So my fault, modulo square. Yeah. My bad. Not real. But the point is that for a Hermitian system is 1. And it's fundamentally greater than 1, and it spikes at these points. And what you see here is the modulus of the eigenvalues plotted as a function of the same parameter. And you see these degeneracies when two bands meet, and you see that they occur at the same places that these spikes occur. So he noticed something interesting, and he says, sometimes k can even diverge when the resonator has exceptional points. And he says it would be interesting to explore. So I really went through the literature, and you have all these infinities in theory. But then when people actually calculate line with this and they try to increase this k, they only measure values of a few hundreds, as we expect. And my goal was to see if I can compute that and if this can be useful, if that can be a useful application of exceptional points. A few hundred, so 300 for unstable lasers. By Siegman and also Wordman measured that, but only 5 or 10, which is still a lot. If I can get enhancement of 10 or 100, great. Infinity, because you see people saying, you know, you have giant excess noise factor, 10 to the 10. But obviously, this will not be real. So now I'll tell you, so that's the goal. My goal is to calculate how much can we benefit from that? And I'll just go briefly over the theory of how people find fluctuation spectra. So I summarized it in 4 steps. And the starting point is Maxwell's equations again. So it's a semi-classical treatment. And we introduce the currents as random driving sources on the right-hand side. This is just Maxwell's equation. Epsilon is the permittivity. And then we could formally solve it by convolving the Green's function with the currents. That's the field. And if we could compute that, then the variance of the field would just give us the fluctuation spectrum. So if we know the Green's function and if we know the variance of the currents, then we have the spectrum. What we need is something to tell us the spectrum of the currents. And for that, we can use fluctuation dissipation theorem. So if the system is in thermal equilibrium, then the autocorrelation function of the currents is given by this product, which is a product of a temperature factor, depends on the temperature of the medium, and in optics on the imaginary part of the permittivity. And this, in principle, is a complete description. So the challenge of computing spectra boils down to calculating this object, the Green's function. So the standard way to do it, if you have a resonator and the modes are non-degenerate, is to do Green's function expansion. Also in the degenerate case, sorry. So the starting point is to think of Maxwell's equation as a generalized eigenvalue problem. So writing it this way, En are the eigenvectors and omega n square are the eigenvalues. And then when the spectrum is non-degenerate, we can expand the Green's function like that. Write the series. And then I just want to point out that this object in the denominator is this unconjugated inner product that we keep seeing. And the reason is that Maxwell's operator is complex symmetric. So that's I'll skip the words, but that's the natural inner product we need to use. And I'll repeat what everybody says. The important property of this quantity is that it's not necessarily positive. And in,
Excuse me.
Yeah.
What is the matrix A and what are the
Curl.
eigenvalues?
So curl. So I just wrote curl. I'm sorry. This is Maxwell's equation. Put a 0 for the noise-free.
Yeah.
Put a 0 for the noise-free problem. Define that as A. It's not essential,
And,
but to write it this way.
Well, what I wanted to ask you was those eigenvalues or
Omega n square.
or real.
Omega n square can be complex. So actually, in this part of the talk, I will focus on passive, so not passive, but resonators that are sub-threshold. They're not lasing, and omega n square can be complex.
Okay. So A is sort of an open system. and that's
Yes,
why-
yes, it's open. Yeah, from the outgoing boundary conditions.
You were using a sort of a
Standard resonator.
Not the bound state
No,
expansion, but
the usual.
When you expand it, you mean you use the resonance.
I'll say quickly. I'll say quickly what it is. So this is curl, and I can write it. I can, if I want to, I can discretize it, and the end take discretization to 0. So curl is a matrix, and epsilon is a matrix, and then I can impose outgoing boundary conditions that they can be expressed inside my matrix. And then En and omega n are just the frequencies. I just solve eigenvalue problem with outgoing.
Well, what I wanted to know was are they resonant eigenstates or?
Yes, they're the usual thing, the standard, the ones that are growing. But
Well,
I will take a
depends on
PML.
the context, so.
It depends. Yeah, I will implement either analytically. So they're not growing because I either do it in 1D and I implement outgoing boundary conditions analytically, or I put my system in a box and I put perfectly matched layers or something to make
Well,
sure.
I just wondered that your bases are complete.
Yes. Yes, I have. Yes. So let's continue and discuss that. If I'm wrong, let's discuss that. Okay. But yes, I'm assuming my eigen spectrum is. Yeah, I'm putting imagine putting your system in a box. So it's not essentially closed. I have a finite world. I put something in the region to make sure if radiation gets there, it's not reflected inside. I have no problem of completeness. And I don't have exceptional points. And let me continue because I won't get... Yeah.
I'm not even going to. This is exactly the CF states that I argued were completed by orthogonal. You're doing it with a PML, but
Yeah.
do it with GANs.
I like the PML thing because there are no questions about completeness. But it is something we discussed for a long time, so let's talk about it later. Anyway, unconjugated product, it can vanish, as we know, and it does vanish at an exceptional point. So my point of my talk is how to do that correctly with the noise. So if we have an exceptional point on the spectrum, this quantity vanishes. It looks like Green's function diverges, but the answer is the derivation is just not valid, as many of you people know, and the reason is that this derivation assumes that the eigenvectors are complete, but they're not. So if we want to have a correct expansion of the Green's function, we need to do something else. We basically need to add more vectors to span the space. So one way to do that is to add the Jordan vectors. So for an exceptional point of order 2, and that's all I'm considering here, but it's not essential. We can generalize that easily. So for exceptional point of order 2, this is how the Jordan vector is defined, by satisfying the chain relations. And another way to think about it is that if an eigenvector E naught is in the null space of H naught minus lambda naught, then the Jordan vector is in the null space of H naught minus lambda naught square. So this is the definition, and if you add that to the eigenvectors, you do get a complete basis. So now I'll show you our derivation of the Green's function at an exceptional point, but we're not the only people who did that, and I can't take, because some pieces of this work appeared in a lot of earlier work. Even there's a work of, so there was this also work presented yesterday. Anyway, there's a lot of work on this, and this is our derivation. It's very simple, so I'll tell you what it is. You can take the Green's function of a system near an exceptional point, at some point where you have a complete basis, and then you can express the modes, which I called here E plus minus and lambda plus minus, eigenvectors and eigenvalue, in terms of the degenerate quantities by using perturbation theory, and I'll show you how. And then you just take the limit of deviation from the exceptional point going to 0, and you get a finite expression. It's just easy to do. That's why I'm still showing you. And then I'll just tell you how we do step 2. So if we want to do perturbation theory near an exceptional point, we need to use defective perturbation theory. So I think, I give it that silly name, but the work was done by Melabayev, I think, mainly. So the idea is the usual idea of perturbation theory. You write your system. Now I'm talking about a system near an exceptional point. So P is my parameter, and P naught is the exceptional point. You just write your Hamiltonian as an exceptional quantity plus a deviation. And then, as the usual thing, we want to expand the eigenmodes of H in terms of the eigenmodes of H naught. So we expand them in a series. But instead of taking the usual Taylor series, we take this, it's called Newton-Poisson series. And it's an expansion in the small parameter that has these fractional powers in the small parameter to have all the properties. And this is the result. So we take that, we plug that in Green's function expansion, we take the limit, and we get a formula. So here is just a comparison between the way the Green's function looks like in the non-degenerate case and the expression for the Green's function near a double pole.
This is first order perturbation. Is that right?
This is first order perturbation theory, but it's enough. There are additional terms in the expansion, but they are lower order terms in terms of contributing to the spectrum. I can comment on that, but it's not so important. But let me just point out the differences. So in the non-degenerate case, we had this unconjugated inner product of the mode with itself. If we do things correctly, we have inner product between the mode and the Jordan vector. We can evaluate that. It's finite, so nothing funky happens. Instead of the simple poles at omega n, we have double poles. At omega 0, that's the pole that I'm considering. So the implication in optics is usually when you take a resonator and you look at the spectrum, you have a set of Lorentzian peaks. What we will have is squared Lorentzians due to this double pole. So this is kind of intuitive, but still not well known.
You could have had degenerate in the normal case.
What a normal degeneracy would still give you, but it's simple.
Just still gives the single.
Simple poles, yeah, and no Peterman enhancement. Because, normal degeneracy you can just span. Okay, so what we can also extract from this that people have not done, but it's not so hard, is just to take the Green's function, convolve with the currents. If we have some now, a resonator with some gain media, we can integrate that and get the emission properties using the temperature of the media. So we can extract some results from this. As I said, many pieces appeared in many previous places, but not so much. People have not really looked at that in optics. So
what is the justification now for using fluctuation dissipation theorem?
Thermal equilibrium. So you can assume. So you can describe both systems below lasing. If they're pumped, they still reach a quasi-steady state, and you can still describe not only steady state, quasi-equilibrium. And you can still describe, if you have gain medium, it can be described as a system with negative temperature. still obey Boltzmann statistics with a negative effective temperature. Do you,
I think this thing has been checked and studied a lot, and it's really
yeah, it's from standard laser theory, but the way I understand it is this. In semiconductors, you say that the intraband transitions are much faster, that basically the system relaxes. You pump it to some population inversion, but then it relaxes to this state, and it's in quasi and local, it's called equilibrium. But that's another point we can discuss later. Oh, wait, but I want to make one important comment. Evaluating these formulas is not that trivial. So if we want to find Jordan vectors of nearly degenerate matrices, it's not that easy because a nearly degenerate matrix is just not degenerate. And we have an additional computational project led by a very brilliant math student, Felipe Hernandez, who has a very neat way to do that. I can tell you, but it's not my idea. So we're also working on that. I can also comment that later that if you want to evaluate my formulas, I can give you a simple way to do it. You don't actually have to compute the Jordan vector, but that's just a detail. So now I'll show you some very simple applications of this. How much time do I have?
More than 10 minutes later, so you have 10 minutes, at least 10 minutes.
I have just 10 more minutes for the talk.
10 minutes and optional. Plus
It's actually 10:20 effective time.
Okay, so I'll go very briefly about that, and I'll just, because I want to talk about the Linewidth.
Okay.
So I'll kind of skip the applications, and I'll just say that we can find exceptional points like many other people, and we can evaluate our formulas and see drastic enhancement and quantify exactly what it is. I'm skipping, okay, because the laser noise is also important. So yeah, we have 1D examples. Simple, and then we also recently at MIT there's a very nice work by collaborators on this project, and they found exceptional points in a passive. You take a 2D photonic crystal, so periodic array of holes in some silicon slab, and you put that in air or in liquid, and they could find that by carefully tuning the parameters of the structure, you can force rings of exceptional points, so exceptional rings in the band structure. So that's the band structure, and we are currently running real-time, realistic simulations and measurements, trying to see what we can do with that. And with this, I'm switching gears to the second part. So this is the work that we did with Doug Stone's group, and it's about lasing. So again, the situation that we're considering is a resonator. We have some poles of the Green's function, and then when we add gain, what happens to the poles is they move up. They become less and less lossy. And at some point, one of the poles can hit the real axis, and then the system will reach a threshold, and it will begin to laze. And as we said already, what noise does is below threshold, it's incoherent. That's everything we discussed right now. But once the system begins to laze, then we have stimulated emission. That's the main source for the resonance peaks. But then what noise does, it broadens these peaks, and I'll talk about how we computed the Linewidth. Okay, so first let me say, why are we looking at this now? It's a very old topic. So basically, before the first laser was built, people were interested in knowing what's the Linewidth, and the first estimate is from '58, from the proposal. And then there was a long list of corrections, but most of the theory on this is for analytically solvable cases, where the modes are basically e to the ikx. That's what most people did, and it was good for the old lasers. However, in the years that followed, there's also a huge development in the lasers, and modern microlasers have these wavelength scale features. I showed here 3 examples. And most of the theories, the assumptions that go into the early theories, don't hold. So if we just take the old formulas and plug the parameters of the new structures into the formulas, we just get wrong answers. And there's a need to have ab-initio tools, something that would be able to handle these geometries correctly, and that's what we tried to do. And I think we did. So let me first tell you what is standard laser theory, laser Linewidth theory. What's the answer? So this is the traditional formula. The first term is called shallow Tan's term. I'm kind of I'll tell you what it is. So omega naught is the lasing frequency, gamma c is the cold cavity decay rate, and p is the output power. So this formula says that the Linewidth will scale as 1 over p, narrow with a strong power. Then there's a correction, the incomplete inversion correction. So N1 and N2 are the populations of the atoms in the lasing transition. If the population is not fully inverted, that increases the Linewidth. Then there's the Peterman factor, and there's another correction called bad cavity correction due to dispersion of the medium, so it can actually reduce the line width. And last, there's this alpha factor. And it's due to the fact that in a laser, the fluctuations in the intensity and in the phase of the field are coupled. And this alpha, I'll get to the definition later. It's not very important. But this was standard laser theory, and there were several generalizations. And the last generalization, like previous to us, was work by Doug and Dong Chung. And they generalized some of these terms, but not all. And what we wanted to have is a completely fully general theory, starting from Maxwell Bloch, that will have all these corrections and possibly more. We wanted to know if we're missing anything.
Is it obvious why the corrections were multiplicative?
They are not, so that's what we're showing.
Okay.
But that's
Then
how people...
Just guessed that it's just a proposal that they were multiplicative.
So for very high Q cavities, so high Q is not lossy, this is a fairly good assumption. But for modern lasers, it's just not. And that's the main point of Doug's paper, and we generalized that. Okay, so the starting point, you've already seen this in the previous talk, is Langevin and Maxwell Bloch. So Maxwell Bloch are a set of equations for the two-level atomic medium interacting with the electromagnetic field. So Maxwell's equations and two equations for the atomic variables, the non-linearly coupled. And then we also have the noise terms again and the fluctuation dissipation again. And here we also need to take into the fact that the temperature for an inverted medium is negative. I can mention also that the imaginary part of epsilon in that case is negative, so the product is always positive. Anyway, it's very hard to solve. So this is a complete description. If we could solve that, we'd have everything. However, it's hard because it's time dependent. We have multiple unknown fields. The equations are nonlinear and stochastic. So this is very hard to solve. How many minutes do I have? 5?
10 minutes.
I have 10?
10 in all.
I'll do well. Okay. So this is a hard problem, but the noise-free problem was solved by Doug, and that's what you've just seen. So he considered the situation when you have no noise and your laser is operating in a multi-mode steady state. So that's what he considers, and he makes one central assumption, and that assumption is that the inversion of the atoms is stationary. It's not evolving. It's a pretty good assumption for most microlasers. He actually went over he defined when, but this is valid in many cases. And with these assumptions, he was able to derive a nonlinear generalized eigenvalue problem. So he was able to write this thing looks just like Maxwell's equation, but the permittivity is nonlinear. It has this saturation term. So you see that this is, a lot simpler than Maxwell Bloch because time dependence is gone and we have just a single equation. It's not trivial to solve, but if we can do that, we can solve. We know what our modes look like and how our system behaves. So they were able to solve successfully and describe random lasers and realistic 3D photonic crystal lasers. And what we wanted to do is to do the same thing for noise. So here is what we did. We gave it a name, N-salt, for noisy salt. And the starting point was to take these salt solutions, which can be found numerically, and then to add to them driving Langevin noises and use the fluctuation dissipation theorem. And then we could derive analytically equations of motion for the lasing mode amplitudes. And I'll show more what I mean, but we derived these dynamical equations, and then we could do one more step analytically, and that is solve for the spectrum. So by some linearization and closed form integration, we solved for the spectrum, and we got these formulas for the line width and for the multimode correlations, which people couldn't solve before. And also we can describe all the features, like relaxation, oscillation, side peaks. I can comment in the end on what we think we don't have, if someone is interested. But first, let me show you what's the result. So this is what the result looks like in the single mode regime. It looks like a generalized shallow towns. It reduces to shallow towns, but these tildes hide the definitions of the terms. They're pretty scary. They're just integrals, though, over solved solutions. So given that you can solve the noise-free problem, you just need to evaluate a bunch of integrals, and you have the line width. And the other point that is important, and that's the point that you brought up, is that since all the terms are in terms of integrals over solutions that include nonlinearity and include non-emission, because they include the boundary conditions, then it's artificial to actually split it this way. And I only split my formula this way to compare, to show how it reduces. Like if you see what he presented the full thing, which might be more physical. But I did this so that people that are interested in lasers.
You can take all the different limits.
Yes, I took all of that's what I did because we wanted to make sure but there's a lot of previous work on this. Okay, so now let me show you one intermediate step, and that is the dynamical equations that we obtain. And I just want to tell you what we mean by dynamical equations. So if we don't have noise, for a noise-free problem, you find the eigenmodes, and then you can expand the field, E, as a sum over modes like that in the usual sense. However, if you have weak noise, you can use time-dependent perturbation theory. So you can still span your field like that, but assuming that the amplitudes are now time-dependent and slowly varying. So this is the standard time-dependent perturbation theory approach. And then traditional laser theory has a prediction for how the lasing mode amplitudes evolve. And basically the idea is that the amplitude evolves like a nonlinear self-sustained oscillator, the amplitude of the mode. So if you have some laser operating with some amplitude A, if the amplitude grows for some reason, the interaction with the gain medium will tend to bring it back to steady state. This is a Langevin force. It was not derived from first principles. That's what we did here, but it's a fairly legitimate model. You have a Langevin driving source and a van der Pol oscillator. So that's what we generalized. We started from Maxwell Bloch, and the way that I showed you, we expanded time-dependent perturbation theory, and we derived this generalized equation. So you see that we have, instead of this instantaneous nonlinear restoring force, we have a time-delayed, spatially inhomogeneous nonlinear restoring force. We have some generalization because the interactions of the gain and the field are not instantaneous, and they're spatially dependent. So we derived something that generalizes this formula. But first of all, it's derived from the beginning, from Maxwell Bloch. And we also, like many other people, we can extract from these dynamical equations certain things. So we can look at the spectrum to noise. And in future work, we hope to also look at stability of the solutions, because we basically know how the system behaves near the steady state, and extract relaxation rates. But now let me show you what we did for the Linewidth. So this is our multimode formula, and I'm skipping. It's just a bunch of definitions. And I'll just tell you that there are some new predictions. For example, instead of so traditionally the incomplete inversion was that factor, but we have basically if the inversion is spatially inhomogeneous, we get a larger contribution. So that's one result.
Oh, you mean but the previous one, N1 and N2 were just numbers?
Spatially averaged.
Yes.
Yeah. I mean, they assumed homogeneous systems pretty much everywhere, and with some exceptions, but yeah. And maybe I'll go on, I think. I'll skip.
But they didn't know to do that averaging that you've done.
Right. They did not do the averaging that we've done. So that's our new result. Maybe I'll also... Yeah, I'll explain it. So another implication is this. So remember the bad cavity, so the alpha factor. So we found some bad cavity corrections to the alpha factor. So what the alpha factor was, so we have a laser operating in a steady state, and then you have some noise. And there are fluctuations in the intensity of the field and in the phase of the field. So the alpha factor was an increase due to the fact that intensity fluctuations are coupled to phase fluctuations. Traditionally, the expression for alpha factor is this, which is omega A is the atomic resonance, omega naught is the lasing resonance. So alpha was the detuning between the atomic and lasing resonance, divided by the atomic decay rate. What we find is some expression in terms of integrals over solid solutions. So we have corrections to this due to the fact that the cavity is open. So in order to test that, we took a very simple case. We took a 1D dielectric slab in air. So this is just some resonator, 1D resonator, and we changed continuously the permittivity or index of the slab. So that essentially, we're changing the index contrast between the slab and the air, so we're changing cavity openness. So when we plot the alpha factor as a function of the permittivity, we see these spikes, and there are some qualitative differences between our factor and the traditional factor. So it could be an important effect.
Are those spikes exceptional points? Or
No,
or
these
they're
are switching. So when you, so cavity, if you just have a 1D dielectric slab in air, the resonance is like a Schrodinger potential well, right? And then when you change the cavity index, you move the resonances around. But we're pumping at a certain, it's a fixed frequency. So as we're sweeping the modes, new modes begin to laze. And every time a lasing mode changes, you get a spike. So there are some qualitative differences between what people have seen and these formulas, which we think are interesting. And I'll just say that we verified in order to make sure we're not missing anything. We took Maxwell-Bloch equations with noise, and then Alex Surgeon and Doug's group performed brute force simulations. And he did this with finite difference time domain, FDTD. And this is the result shown here. This is the Linewidth as a function of the output power. And the simulation are the purple triangles. And then our theory is this green line. And you see that the other formulas are not doing as well. So we're happy about that. And I'll just say that what you see here is the spectrum for a laser that is operating at a regime where you have sidebands. And we also have a formula for that I haven't seen. And there's some qualitative agreement, I think. And this plot shows so just the alpha factor, and the blue line and cyan line are without an alpha factor, with the traditional alpha factor. And again, there's a good match. So what we'll
I see more than 3 peaks in
these ones, so these are higher order peaks. So we took these ones. Yeah. So these are higher order peaks. So basically what happens in a laser, you have, it's operating at a steady state, but every time you have noise, you have relaxation oscillations. And the relaxation oscillations, this frequency is the relaxation oscillation frequency. This is again the same quantity. It's like a frequency comp. Harmonics. Yeah, but the only thing that we thought we can learn, our result here was that basically we described the full thing. That whatever is in Maxwell's block is in our theory. And I don't want to bore you, so this I can for sure skip. We did a 3D example. And yeah, I'll tell you what we want to do with this. And with that, I'll finish. We want to combine the first part of the talk with the second part of the talk. So what you've seen in the first part was exceptional points below threshold. What you've seen in the second part was noise above. And I have some ideas and results on how to treat exceptional points above threshold, but this is work in progress. And we want to extend this theory to study various things like amplified spontaneous emission near the threshold regime. And that will give us a laser theory for diodes, which Doug pointed out. And we think we can do it the same way. And another thing we want to extract from this is analyze stability and see, since we have very simple equations, in what sense will they give us an answer to stability of nonlinear PDEs.
Thank you. We have time for one quick question because we are 15 minutes beyond schedule.
I have a quick question. But,
But you already asked 3 or 4, so maybe.
This quota is complete.
Well, I'll take one back.
It doesn't work this way. Anybody? Okay, so.
Okay, it's actually a very general question. It's very unfair for me to ask it at your talk. The whole approach here is to take the Maxwell equations and wherever you see a polarization that's a constant, to replace it by a function of x, and to take it complex if you want, and then solve that theory very, very well, which is what you just did. But my question is, where do those equations come from? Because if I start with an action and I want to obtain a spatially dependent polarization and I put it in the action, then when I do the variation, I'm going to pick up derivatives of the polarization as well. So it seems to me that these are some kind of phenomenological equations which may not follow from a full covariant theory. And the question...
These are not covariant, these are in medium.
No.
Medium.
I mean, it may not follow from the variation of an initially covariant action the way the Maxwell equations do. And maybe you can reach a point where you might actually become sensitive to derivatives to a contribution of a derivative of the polarization somewhere else in the equations of
In
motion.
statistical mechanics, it's called mean field theory and coarse graining, and you can always improve.
But you can include gradient. That's
Yeah,
what I'm
that-
saying.
I'm saying
It's
that
gonna be-
yeah.
coarse graining
Yes, so you have gradient expansion.
Yes, I would have expected gradients just from starting to an action.
But
So
I'm
I'm
not.
curious to know, because I mean, I've been
But
listening to this conference.
don't ask me, ask them.
Yes, that's what I'm saying.
I'm not to be blamed.
Gradient. There is no local effects, of course, in
Yes.
the medium.
But why is all this not sensitive to it? That's the question.
It's not that it's not
Well, there are two
sensitive.
different gradients, okay? One of them is polarization is the linear response. So this is well beyond that. This is a nonlinear
Yeah.
polarization. So we're taking into account, and that's actually all the physics is dominated by that saturation. As I said, you can't even make sense of this theory without that saturation because you have infinities on the real axis. So that's, I think, the big contribution of SALT and now NSALT. So we do it correctly with the saturation. Now, non-locality just depends on ratios of wavelengths to structures and so on. I mean, we have you have to look at whether you're really averaging over things or not. But people could put non-locality into it.
Epsilon doesn't have to be a function of position, right? Epsilon of R can be a function of R and R prime. The kernel, with a kernel which relates polarization.
Yeah, epsilon can get more and more complicated. It can be non-local in space and time, and there are cases when you need to do it.
When you start solving the simpler problems.
Most of the time, this is right. I mean, this is, if you look at laser theory, believe me, we're doing a lot more than they usually do.
Okay, guys, it's at your coffee's expense, so okay, I think we could cut off now, and thank you so much for the